Hey everyone, my name is Riley. I am the Director of Integrations Engineering at Quai Network, and today I'm going to be talking to you about multiplying developer impact and speed for global adoption. So basically what that means is, in a word or in a sentence, the better the tools, the more we can do, more developers can do in less time. Okay, and that's kind of our whole design philosophy, right? That's how we're approaching this. And so I'll give you a little bit of background on Quai's architecture, kind of the complexity of the system and how we think about building tools for this complex system. Okay, so let's just get right into Quai Network's architecture. Okay, so first of all, Quai is a monolithic network, meaning that we're not scaling using L2s or kind of external networks built on top of ours. We are using horizontal sharding for our scaling. Okay, and the horizontal sharding actually is dynamic, meaning that we just launched mainnet, first of all. Okay, like we just got listed on exchanges last week, and right now we just have one shard. Okay, there is a hierarchy which I'll get into in a minute, but the shard is the execution space that we're using, right? And each shard can handle anywhere from 5 to 800 TPS, and at a certain rate, if there's congestion in the network will say, okay, we've had sustained congestion, we need another shard. We need to offload some of that demand and match the supply so that we don't have a situation where our fees are just atrociously high, basically, forever. That's what we're trying to fix here. And the network can actually shard up to 256 times, right? So you can imagine at that level of TPS times 256, it's kind of fulfilling the entire need of the global economy as it currently stands. So we're not going to be there for a while, but just to give you an idea of how this network works, it is totally dynamic. Okay, and so the hierarchy here is what orchestrates that sharding mechanism and how we allow that to happen and how we can transfer state across these sort of execution shards, right? So basically at the very highest level, we have the prime chain. The prime chain orchestrates the far-reaching state transfer of these different execution chains. Okay, so then we have region right underneath prime. You can actually sort of think about this how data centers might be structured for cloud providers, right? They have regions, and within regions they have sort of sub-regions that you can use, like US East 1, US West 1, US East 2, right? So you can kind of almost think of it in that way. And eventually, it's very likely that these subnets kind of geolocate close to each other because the final boss of scaling is network latency. You can't get around it. That's the speed of light, right? And if you're having to make multiple round trips across the Earth, you're gonna have a slower network, right? There's just no way around that. These are the laws of physics that we're bumping up against here, right? So basically, you have the prime chain underneath region chains, and then region chains actually each have these zones, okay? And so zones are more akin to US East 1, US East 2, right? They're in the same region, and they kind of can talk to each other with low latency, but they're different. In our case, they're different execution spaces entirely, right? And each zone actually has a sharded address space, meaning that, and so let's talk about a specific one right now. So our current region that we operate in is Cyprus. And there's Cyprus 1 is the first zone in the Cyprus region, and that's all that the network is composed of right now. Prime, Cyprus region, and then Cyprus 1 zone within that. Okay, so if let's say there's an expansion and now there's Cyprus 2, and I want to make some transaction starting in Cyprus 1 and maybe transfer some state over to Cyprus 2, whether that's a smart contract call, whether I'm sending Quai, what have you, I can actually just do that, and the region that I'm within helps me orchestrate that state transfer, okay? But imagine we've expanded several times. Now there's several regions and several zones within each region. Imagine if I want to start in kind of zone 1, region 1, but I want to make a smart contract call in like region 5, zone 3. Well, that might need to go up through the region chain, up through the prime chain, down to the other region chain, and into the zone, right? This is how this hierarchy sort of manages this trustless bridging between these execution states, right? And so, as you can see, that's quite a bit of complexity. Most developers are mostly concerned with these execution shards, right? They don't want to know about trustless bridging. They don't need to know the mechanisms. They're just like, hey man, I want to like deploy some smart contracts, and I want to like point my dApp to some smart contracts. Like that's my intent as a developer, right? Not only do we have that architecture, but we have a dual token system. Okay, not just dual tokens, dual ledgers. Okay, the Quai ledger, EVM, account-based ledger, similar to what we're all familiar with in kind of EVM land. And we also have Qi, which is a UTXO ledger. Okay, these ledgers are co-located in each shard. Every zone has a Quai ledger and a Qi ledger, right? The Quai ledger, programmable, do whatever we want, smart contracts. Qi is a strictly denominated UTXO-based ledger. But why strictly denominated, right? That's kind of what we're trying to build with Qi is privacy-preserving cash. We want this to be electronic cash. We think that there were a lot of claims early on in the crypto space that said, we're going to build peer-to-peer cash. And then kind of nobody did it really, like especially at scale. And so we thought that the UTXO ledger with strict denominations is the best representation of cash, and it has really good privacy preserving qualities as well. Okay, so when I say denominations, think of it literally as a dollar bill. I have a $5 bill. I can't subdivide that. I can't like multiply it by 2. It's always going to be a $5 bill. Okay, same with chi. I might have a 5 chi denomination. I can't like split that in 2 and get 2.5 denominations because a 2.5 isn't a denomination. You get 1 chi, 5 chi, 10 chi, 100 chi, and these must be used similarly to cash. If I go to a store, something costs $13, I have a 20, I give them the whole 20. I don't give them 60% of it, right? And then they give me my change back, okay? And so this is structurally the same way that chi operates, right? But chi also has this really interesting feature for privacy, which says in UTXO, I'll give a brief kind of overview of how UTXOs work in general before we dive into this. So for UTXOs, you have transaction inputs and you have transaction outputs. Let's go back to the store example, okay? My transaction input in this case is a 20. Like I said, I have to spend the whole 20. Can't spend only 60% of the 20, I have to put up the whole thing, okay? And let's say the output here still is gonna equal 20. Okay, it has to. The fee, we're gonna ignore the fee for simplicity's sake, but the input is going to be equal to the output. The output is gonna go to somebody else, right? Very similar to how money works, and then I'm gonna get some change back to me. Okay, but the rule is, for the outputs, you can't have the same address more than once. Okay, so let's look at a specific example using denominations. I need to pay someone 13 chi. I have a 20 chi denomination. I'm gonna put that whole thing up as an input, and then I'm gonna give them 4 outputs here. They're gonna get 1 10 chi, and they're gonna get 3 1 chis, okay? Because it's cash-like. You have to do these all at once. So there's 4 of those outputs to them. But then there's also 3 outputs to me. I'm gonna get a 5 chi, I'm gonna get 2 1 chis. Okay, so we've actually created quite a bit of outputs for this one single input. But like I mentioned about the outputs, every output needs to go to a unique address. Okay, so let's think about the regular paradigm. I want to send anybody some Quai. They just give me one address, and I send it to that one address. Pretty easy. In Bitcoin, UTXOs are of arbitrary denomination, meaning that any given output could be 100 billion Bitcoin, or it could be 0.00005 Bitcoin. There's no rules. It's arbitrary value, right? So it doesn't have to be in these strict denominations. Okay, so how does that work? When I say, I need you to give me some amount of addresses so that I can give you some amount of outputs. But the thing is, you kind of run into a chicken or the egg problem. I don't know how many outputs until I have actually constructed my transaction and said, here's how I'm gonna split these inputs into these outputs. And now that I know that I need to send you 4 outputs, because I did the math and I checked, that said, you're gonna get 1 10 chi and you're gonna get 3 1 chis. Great, now that I know that, I want you to give me 4 addresses. But I kind of already wanted your addresses already before I started doing my transaction. That's kind of how that works, right? So you kind of run into a weird UI experience here, but we fixed that with our tooling, and we'll get into it in just a second. But now that we've kind of gone through this, the complexity is high. But the problems that are being solved require some reasonable level of complexity, okay? And my job is to make sure our tools account for the complexity, and they allow the developer to focus on intent, not on architecture, and I keep saying intent, and let me clarify intent. Intent is what I want to do and focus on what I want to focus on. Anything required of me to consider outside of my intent should be masked away from me, okay? That's just too much complexity for me to care about. It actually just kind of takes up too much of my brain space. So with that, let's get into how we think about these design principles. Okay, when we're building, we're really kind of focusing on this rule here, which is the greater the complexity of a system, the better the tools have to be to account for the complexity. That's basic complexity math, right? Like if we think about this concretely, system A, very high level of complexity. System B, low level of complexity. If I were to build a tool set that allowed a developer to, with the same number of line of codes and same sort of cognitive load, do the same outputs on system A and system B, The tools for system A have to be better, right, to account for that extra complexity. Okay, and so that's kind of our biggest design philosophy. Philosophy number one, reduce the cognitive load. Anything outside my intent gives me cognitive load, gives me cognitive burden. I don't want to consider my sharded address space. I don't want to consider my sharded execution space. I don't want to consider how trustless bridging works between these execution shards. I just want to send Quai. I just want to deploy a contract. I just want to interact with a contract. These are my intents. Everything outside is burden. Reduce the burden. And everything is going to really kind of come back to this number one principle. Everything can boil down to, if you reduce my cognitive load, I can do more with less in less time, right? So number two is reduce the number of steps it takes to complete a task. This is kind of a basic one, but it's kind of something we take for granted a lot of times in good tool sets. If I want to just send Quai, not unique to Quai, this could be any EVM. I say, I need your address, okay? And you're going to send me your address. And I'm going to say, I'm going to send you 10 Quai. Those are the two things I care about. But those aren't the end of the road. I also must estimate gas on this transaction. I must see what the gas fees are like for this transaction. I need to know how many transactions I've sent so that I can populate my nonce properly. I need to know which chain ID I actually need to populate this so that I can effectively, prevent replay attacks. And then by the time you kind of check through this list, you're like, damn, there's kind of a lot of things that go into that. And I don't want to go through every one of those steps. I want to go through one step. I want sending this value to this person. Every other step should be handled for me. This is, in regular EVM-based tool sets, this is common. Okay, a lot of times it will populate under the hood what needs to be populated for me if I don't supply it, which is great. We also abide by these rules. But you can imagine with Qi, there's a lot more steps here. Like we just explained to the store, first of all, I need to sync with the network. I need to find all the addresses that have any balance. This is not account land where my one EVM address holds all my information. It's sort of like my passport to getting paid and paying people. It is not like that in UTXO world, okay? UTXO world has many addresses. And some can hold several UTXOs. They might hold one UTXO. They might hold 0. Who knows? I need to first find that. Okay, so just providing a user to say, hey, okay, sync my wallet. That's it. Wallet.sync. We've done that for you. We've gone, we found all of these addresses for you, all of these UTXOs you have, and effectively said, add them all together, that's your balance. Do whatever you want. Then I need to say, okay, but all I want to do is I want to send person A value B. That's all I want to do in Qi, right? Like I don't want to have to go and do that change making problem where I say, okay, it's going to be 13 Qi, but I only have a 20, but actually I also have 3 5s. So like, am I going to choose 3 5s? Am I going to choose 120? And then based on what I choose there, the outputs are going to be different, right? So you kind of have this change making problem, which is a very common problem, of course, but one that must be considered. Okay, so again, making these interfaces uniform. If I want to send Quai, wallet.send. If I want to send Qi, wallet.send. Has to be the same. The number of steps you skip using our tool set under the hood for Qi is unreal. Okay, and in a second, actually let's get into it right now. The next thing is be opinionated but not limiting. So let's talk about that UX problem we talked about with Qi. Okay, if I want to send you something, I first need to construct the transaction, even figure out how many addresses I need from you. Okay, that's like a pretty shitty user experience when you think about it, because how do you give it to me? And also, if you're going to give it to me first, how do you even know how many to give me? Okay, am I going to instruct my transaction first and then scan your QR code? How would I even tell your QR code how many addresses, right? Like in a normal, regular, unthought out solution, you might just say, give me 100 addresses, just in case. I don't know what I'm going to need, but just in case, give me as many addresses as I might need. Okay, and so we said, that's horrible. There's obvious chicken or the egg problem, and you don't want to oversupply addresses because you're kind of divulging too much information at that point, right? If you're saying, here's these 100 addresses, even if I just need 2, you just gave me 98 of your other addresses that I can easily track and attribute back to you. Bad news. So we actually use this thing called payment codes. Okay, so we said, how can we make Qi feel like EVM land, where you have this one sort of identifier that does all of your stuff, that you pass to people, that people pass to you. Let's make it feel native. Okay, so what payment codes do is they'll actually allow me to derive your addresses for you. Okay? I know that sounds crazy, but I can't know your private key, but I can make your public key. And from your public key, I can make your address. And then you can actually find that address and its private key. Okay, so we call these payment channels. So basically the flow would be, if I want to send Christopher 10 Qi, what he's going to do is say, cool, here's my payment code. I'm going to say, great, I'm going to take that payment code, and I'm going to construct my transaction. I'm going to find out that I need to send Christopher 4 outputs, and I need a unique address for every output. So what I'm going to do is I'm going to derive 4 addresses for Christopher, only knowing his public information, and I'm going to send him that transaction. So he, at this point in time, does not know about these addresses. I then send him my payment code, and immediately he can derive those exact same addresses and get the private key information to be able to spend from those addresses. So what this does is it actually restricts me and you devolving information about each other between us. Nobody could derive those addresses I just derived with Christopher because they'd have to have my payment code information to do it. So what you do now is you create channels with people, and you can actually just keep addresses derived in that channel between you two. And nothing about your payment code is indicative of any other address on chain. Okay, so you're very obscured away from what's actually happening. So now, from the outside perspective, the user just says, yeah, I have this one identifier. It represents my whole wallet across every single shard, no matter what. And all I have to do is say, hey, Christopher, I'm going to pay you. I'm going to pay you 10 sheep. Where do you want to be paid? He says, Cypress One. Great. That's it. That's all the developer thinks about. And then everything else under the hood, the many, many other steps involved with constructing this transaction in a seamless way is totally handled for you. Okay, so like reduce cognitive load, reduce steps, be opinionated, like I said. And the opinion in our case is that we think the better user experience is payment codes, not supplying 100 addresses up front. And we build all of our tools to express that opinion. We're not going to say you can't supply 100 addresses up front. You're just going to have to do more work. Okay, we're not going to limit you to force you to use this sort of standard we've built. But again, all you're going to do is put more work on yourself and increase the complexity and your own cognitive load. Okay, so be opinionated, and your opinions as a tooling developer are expressed through interfaces. The default easy path is my opinion of the best if I give you a tool, right? Because that's the only way. I can sort of guide you to this path of how should you use my tool. Well, you should use it like this because I think it's most optimal either for your use case or for the network. And either way, that's my opinion. And I'm kind of instilling that into my design, right? And the last thing here, complement the existing workflows, okay? Developers have workflows. We don't need to uproot developers and say, okay, cool. If you want to do something for us, if you want to build on our network, you actually have to go learn all this new shit. Nobody wants to do that, right? This is not unique to Web3 or crypto at all. This is how to be a good Samaritan in the tool building space. Okay, if there's like a slightly better way to dig a hole with a shovel, I'm not going to give you a shovel that you have to use your feet for, because how would that make any sense at all? I'm just going to design a shovel that you're used to shoveling with. It's just going to do better for you, right? And these are really like our guiding principles of how we think about building better tool sets. Okay, there's so much copy pasta going on. You just really got to make sure you're not building a moat around yourself before you have anything to build a moat for. Okay, if you make something prohibitively challenging to actually use out of the box, no one's going to use it. No one. Okay, so like everything that we just talked about here, we forked ethos.js, left pretty much every single interface exactly the same, and packed all of this under the hood. Users don't have to learn new tools. They're like, oh, well, I don't know how to use Quai. I'm like, well, have you ever used Ethos before? They're like, yeah, that's my primary package that I use for, dApp development. I'm like, great. It's the same. It's the same. There are no structural changes here. We had to extend it for Qi, but we kept the interfaces similar. So now you're just learning one extra method, and it's called sync. I just need to sync my wallet, and then I can send, right? It's the exact same. So we think building moats or building bridges to people's existing workflows and their existing lives is the way to do it, okay? And so we went even a step further here and said, well, some people don't even want to use Quais. Even if it's familiar to Ethers, they don't even want to necessarily use that. They want to keep using Ethers. They want to keep using VM. They want to keep using WAGMI, right? How can we support those workflows with all this complexity, right? And so basically we adapted our client, our actual nodes that we're running, along with our wallet, Pelagus, to make sure that things actually just work out of the box, okay? Like imagine if I just copy over Compound, okay? And I want to like deploy Compound on Quai or Aave or anything, right? All I have to do is get those contracts deployed using some of the easy tooling that's hard hat, again, very familiar to people, to deploy those contracts. It handles making sure your contract deploys in the right contract space, the right address space for the zone that you actually are trying to deploy to. You don't have to worry about it. You don't have to populate gas. You don't have to do any estimation. You're just like, cool, here's my contract. Here's the contract ABI and bytecode and deploy. That's it, right? So we actually just made that to where once you get those contracts deployed, your DApp is pretty much drop in. If it uses WAGMI, VM, ethers, whatever, doesn't matter. You drop in, and if you use Pelagus, everything works. No additional outside tooling needed, right? We want to make this number 4 very salient to people so that they understand, no, we want to work for you. We want to make sure that all the stuff you know is not for nothing. If you want to come be a developer on Quai, everything applies that you've already known. We're not reinventing everything you know. We're just reinventing the protocol and what we think to be the best way to build a global monetary system. That shouldn't be a burden on you. That's the burden on us. Okay, so we've been talking about a lot of tools and how we think about tools today. But let's talk about tools tomorrow. What does that mean? What does the future of tooling look like in this space? Is it going to be more copy pasta? Is it just infinite forks of ethers? Hopefully not. But what we think is that tools for a decentralized environment should make you more decentralized. Okay, let's think about okay, first of all, don't kill me. That says IPFS. I knew that would be a point of contention here, but I'll explain. So, first of all, we have this really interesting property that we actually came up with one of our advisors. His name is Dionysus. He works at a company called Common Prefix, and he is an academic researcher. And he actually came up with this idea, I think 5 or so years ago, of NepoPows. And NepoPow stands for non-interactive proof of work. What does that mean? Who even knows what that means? Okay, so if you want to get data about the state of the chain, could be balance, could be what is the contract bytecode deployed at this address, it could just be anything about the chain. I'm going to ask probably Infura, going to ask some large node provider, maybe QuickNode, maybe someone else, and they're going to give me data. And I'm probably just going to trust it because there's no alternative. Data providers are one of the most centralized vectors in all of crypto. And we have this whole mantra of don't trust, verify, but then we just forget about that for a second and plug all of our dApps into something that we trust, but we can't verify, right? I could say, what's my balance? It could say, you have 100 Quai, or you have, in this case, 100 ETH. I could say, that's great, I'm rich, I got it made. But really, someone just stole all that ETH, I have 0 ETH. And that thing just lied to me. Okay, so that's why we actually have brand names behind data providers. They want you to trust them because they can't let you verify. The only way you can verify nowadays is to run a node. And presumably you don't have to trust yourself. You think you're operating in your best interest and you should be. So that's the only way to verify these things are correct. That's where NepoPows come in. Okay, so NepoPows actually take into account the work that was done in the proof of work chain in order to prove or give you a proof that what they have given you is the truth. Okay, and then what's going to happen is the Quai's SDK, every time it makes a request, it's going to say, is this proof correct? It's going to validate it for you. And if it's not correct, it's going to be like, hey, big error. Someone's lying. This is wrong. Okay, the data you have is not the data that is true. And it's going to raise the alarms. Okay, so what this actually enables is every single node operator can be a part of a distributed data providing network. No need for Infura. No need for QuickNode, right? You don't need to worry about this one service to get all of your information for anymore. The Quai's SDK can say, we have a registrar of node providers. I can route you to anyone at random, and I can verify that they're telling you the truth every single time. And I can actually aggregate. I can source from multiple providers from this registrar, and I can validate all of them are telling the truth. And even more than that, I can track when they don't. And I can update the registrar, and I can say, this guy actually lies about 60% of the time. He gives wrong data, right? Whether that's him being malicious or whether that's him being out of date and not operating properly, everyone should know about that, right? And so now you end up with this fully decentralized, almost marketplace for data that you can actually verify without having to trust, right? This is a big unlock for us. The other one, the point of contention, I know this is going to be a tough sell, but here we go. Contract metadata. How does this work now? How do I get an ABI? How do I get source code? How do I get any of this stuff? Etherscan. Practically the sister company to Infura. Interesting. Who else has it? No one. Oh, interesting. So if I want to know how to interact with a contract, I have to use this service. And it's true for Ethereum, but it's also true for L2s, right? Like a lot of L2s use Etherscan. So basically, Etherscan now is a systemic part of this entire round trip for developers. Okay, how am I going to know what contract methods are exposed without going to Etherscan and getting their ABI? Unless I deploy the contract, which, generally speaking, is not always the case. Okay, so what we're doing, and of course we're open to getting rid of IPFS here, but we're going to use IPFS here in the short term, is whenever I upload a contract, we actually built it into our toolings right now. So if you're going to deploy using any of our tooling, which we recommend doing because it does these things for you, right? It goes back and it reduces your cognitive load and it complements your workflows. You don't have to worry about it, so you should use it. And what it's going to do first is it's going to get your ABI. It's going to upload that to IPFS. It's going to get a content hash back. It's going to actually, when it deploys your bytecode, it's going to stick the content hash right in that bytecode. Okay, so now what you have is a system where if I have a contract address, all I have to do, get the bytecode from the network, which I can verify they're telling me the truth about because I have NEPO pals, and then I'm going to parse out that content hash at the end of that bytecode. I'm going to ask IPFS to give me that ABI, and now I know how to interact with every single contract on the network, no centralized provider. Okay, so like all we're trying to do here is we're looking at the centralized bottlenecks and we're just like, okay, that's stupid. Let's fix that, right? This is the whole ethos of everything we're trying to build here. Global monetary systems cannot be built on the backs of one single company to provide all of the data. Isn't that a bank? Right? Isn't that what banks do right now? Aren't they the ones responsible for telling us what is true and what is not true? And we just trust them without being able to verify? Not anymore. Tools of tomorrow, they decentralize for you. Next thing, obviously, we're in the AI era here. Everyone at this house knows that this is the case. And so how do you build your tools to be on track with these, right? To support them. First is easy, and it's honestly underlooked. Make your docs indexable. Okay, if an AI can't look at your docs and grab the data it needs to be able to inject into this prompt, it can't use your tools. Okay, this is important for two reasons. It's important for agents, of course, but it's also important just for developers. Okay, I'm not sure what IDE you all are using, but there's Cursor and there's Windsurf and there's Replit and there's Claude Code and there's every single thing that can do so much work for you. And if we're talking about empowering developers, we're trying to maximize their impact and make sure they can do things more impactfully, more quickly, then we have to assume that AI is going to be a huge part of this. We have to build our tools so that the AI can do the work for you better, right? And so that's a really big part of this. So making our docs, we have GPT indexed everything. You can search everything throughout the docs on the docs site, right? So we're fully indexable, and we're trying to make it as easy as possible for people to be able to say, hey, IDE, Cursor, Windsurf, Replit, whatever, I'm using Quai's, the SDK. I want it to do this, this, and this. No hallucination needed. It does exactly what you want it to do because it has the context it needs to be able to do that. Okay, and the next one is obviously agents, and I think that agents are kind of a big part of what tomorrow is going to hold for a lot of us, and I think we're unsure how that might look, but all I know is that if they're the tomorrow that I think I'm going to be a part of is going to be really run primarily by agents in a large way, I want to make sure it can access my Quai and do things for me on chain, right? Which of course everyone is talking about this right now, but there's so many protocols, like there's NCP, and you can make sure that your tooling is tooling that can be used by agents, which is not the case out of the box, right? You have to build these things sort of to support all these different protocols that these agents are using so that they can standardize and they can actually take advantage of your tools, right? I don't even have to send Quai anymore. My agent can send it for me, right? He can make my smart contract calls. He can automate my back office stuff that I need for my smart contracts to operate in a business fashion, right? All of these things are very important about going back to all those design principles. My cognitive load should not be taken up with back office tasks for running my smart contract based business because my AI agents can do it, and they can do it because we build the tools for them to do it, right? That's a big part of it. So I think that everything we've talked about here boils down to complexity, complexity, complexity. And if you're going to take that complexity and you're going to show it to a developer, you're going to do it wrong, and they're going to do it wrong. And you have to empower them. And the people that actually make this valuable are the developers, right? If you have a system, a distributed network, a programmable anything, and you don't think about the developers who are going to program it, you're not knowing your users, and you're not empowering them to actually use your product as well as you could. Okay, so that's pretty much our entire thesis here. This is the end of this presentation, this slide deck. I'm happy to talk about any other thing you want to talk about. If you want me to dive deeper on what Quai is, the energy dollar, Chi, any of that stuff, let's just talk about it, right? Like whatever y'all want. Want me to go back? Whatever.
I would like it if you could kind of expand a bit on the energy dollar. Like, what if you could explain that a little bit? That would be awesome.
Of course. So basically, we have two ledgers, like I mentioned. We have the EVM ledger for Quai. It's programmable. The smart contracts live there, everything else. But Chi in its own separate ledger. And the reason that they're actually separated by ledger, A, is because we wanted to have cash-like privacy and denominations, which you can't really enforce as well in an EVM ledger because we want it to be 100% uninscriptable. We don't want any data attached to these things. We want a 10 Chi denomination to equal a 10 Chi denomination no matter what, like happens with cash right now, right? If I'm gonna swap a $10 bill for a $10 bill, there's nothing I can do to that $10 bill to make it worth more than that $10 bill unless, Oprah gave it to me or whatever. But that's why we decided to do that. So from the actual energy dollar perspective, let's kind of talk about some of the mechanics. Since we're a proof of work network, okay, the only important input into our network is energy. And it's described through the relationship of energy input equals hash rate equals difficulty. Okay, proof of work networks adjust to increases in energy input, aka hash rate, to make it either more challenging or less challenging to mine something, right? So what does Chi do? How does that work with Chi at all? Well, Chi has a very complicated controller between Quai and Chi that basically says, for Chi specifically, let's look at the difficulty of the network and the historical difficulty of the network, and let's also look at the conversion rate, the market conversion rate between Quai and Chi at the time. Okay, and basically what Chi does is as energy input into the system grows, you're going to see a reduced amount of Chi emissions coming into the market. And the reason is a Chi has a number of hashes that it is required to produce it, okay? And so if you say hashes actually have a cost, if you really break it down far, all right, you can price things in kilowatt hours, based on your local electricity market, and then you can say, okay, let's break that down even into our lowest level, which is one hash costs X amount of energy, which costs X amount of dollars to get that one hash. If a Chi, for example, takes 20 hashes to produce, you've effectively created a floor price for Chi that says it doesn't make sense from a market perspective to actually buy this Chi or sell this Chi for less than that market rate of electrical input, okay? And then as the electrical input increases in the system, meaning more hash rate comes online, the controller accounts for this and says, okay, it used to cost 20 Chi, now it's gonna cost 50 hashes. It used to cost 20 hashes to produce one Chi, now it's gonna cost 50 hashes, okay? And that's to account for the increase in supply into the system of energy specifically, which then reduces the rate of supply increase for Chi to account for that new sort of floor price, right? And then as hash rate goes back down and there are fewer hashes in the system, then we're going to increase the rate of emissions of Chi by saying it now costs less hashes to produce a Chi. Okay, now that there's less energy in the system, the hash rates come down, it's easier to produce a Chi because on average there are less hashes available in general. Okay, so the mechanism is more tied to just what is the state of hash rate in the network. So it's not a peg. It's not like, oh yeah, we track regional energy costs and we just like manipulate supply and demand to like stay with those regional energy costs, because energy costs are so micro-regional, right? Like you can't effectively do that at scale. And so what you can do is you can average the global input and just say, actually, hash rate is a pretty good indicator of electrical input, okay? And as hash rate is cheaper, or electricity is cheaper, the hash rate will grow. As electricity is more expensive, the hash rate will decline, right? Which basically accounts for that external market condition of what is the price of hash rate, assuming people act in sort of like a rational manner, which in aggregate for markets they do.
Okay. It's very interesting take on it. How about, all right, the energy dollar is, do you have an energy dollar on both? Yeah, I know you have the account-based ledger as well as UTXO. I'm just kind of wanting to double click into the privacy preserving aspect.
Mm-hmm.
Is there, which ledger is the energy dollar, or is it both?
So the energy dollar is Chi, which means in the UTXO ledger. Okay. So these two ledgers are fully separate, but there is a native protocol mechanism that allows you to convert between both. Okay, but if you're talking about, if your question is kind of getting to like, how do I get chi in the EVM ledger? Like, what if I want to use chi in DeFi? Or like, what if I want to use my chi as collateral for a loan, for example? You can wrap it. Okay, so we will have wrap chi. We've actually already built this. This will be deployed very soon. Chi comes online in about a month. So when chi comes online, you can actually deposit your chi directly into a precompiled smart contract on the chain. That precompiled smart contract abstracts all of that fragmentation of denominations that I just spoke about and allows you to use chi as if it's an ERC20 token. Okay, so you still have the underlying value, you still have your underlying privacy here. You still can, transact chi in any way you'd like, but when you're in the EVM space, you want to be compatible, right? You want to make sure that you're interoperable. You want to make sure you're adhering to those standards as well, which goes back to sort of our tooling philosophy being applied here, which is don't disrupt it. Yeah. Let it plug and play, right? If you don't let it plug and play, the adoption rate is going to be very low. And it's going to take a very long time. And so because we want to roll it out quickly and get people on it quickly, we want to plug into the existing standards.
Awesome. On the UTXO ledger, the privacy model of it is the difficulty in, tracing those addresses, like you mentioned with the pay ID.
Yeah, and it's kind of sort of like a one-time use for an address. It's kind of like the way this progresses. So like I might have 10 addresses that hold chi. Once I send them again, I should never send them back. Okay, which also makes it kind of hard to link because these things are not, I'm not having an address that has funds and then it sends funds to you and then you send funds back to me at the same address. Those are very pattern traceable, right? These are like one-time use Visa cards, you can think of it, right? Like we're going to send some funds to an address and then once that address has been used, we don't want to use it again. And that's a privacy standard that like even Bitcoin tries to enforce as well. Any other questions?
I think I'm still digesting. There's so much stuff.
There's so much stuff, and we didn't even get into all of it, dude. We didn't talk about Poem. We didn't talk about work shares, nothing.
When you say dual token system, you typically get the comparison to Terra. So I guess I was curious if you kind of go into like how we're different and how we've been built from a philosophy and from the actual evidence and example of what happened to Terra and how they will.
Yeah, I haven't studied Terra super hard, and because I'm not like at the protocol level, all I can do is talk about structurally how I believe these things work. So with Terra, what they were doing is they were actually promising yield that was not in the system. So effectively, they were using UST to collateralize Terra, right? And when you collateralize something, you better make sure the thing you're collateralizing with it itself is collateralized. And that's what they did not do. So Terra basically said, yeah, like we're going to give 20% yield on UST to make it very attractive for people to come in and hold UST and increase the supply of UST so that we could actually have a sort of liquidity backstop for Terra, okay, which is structurally sound as long as UST is always fully collateralized. But because they were promising a 20% APY on Terra, or on UST, excuse me, they were effectively issuing UST that didn't exist, which basically at a certain point makes UST pretty insolvent, and you don't want an insolvent currency to be your liquidity backstop propping up another currency. And so Quai and Chi are separated. They're natively convertible to each other in the protocol, but Chi does not depend on Quai, and Quai does not depend on Chi. Okay, Quai is a sort of like deflationary token that over time, like supply is capped, and we don't want it to continue growing to infinity. It's a gas token. It's supposed to be deflationary, mechanistically similar to ETH. Chi is like fully. They're not even in the same like ledger, right? It's not like I can just like say, oh, I can only have a Chi. Right. So that's a big part of this. And Chi is being emitted based on, yes, its conversion rate to Quai, but also the difficulty in the network. Okay, so like the difficulty in the network is the primary input determining the emission rates of Chi, because that is determining the electrical input into the system in general.
Perfect.
That's good.
So another one, I think if we don't have any more questions about Chi, we can kind of move into like some of the mining things that we've innovated on. Yeah, so another big one that we've innovated is called Poem, right? That's our consensus mechanism. So if you know Bitcoin consensus, it's longest chain rule, which means that imagine two blocks are sort of proposed simultaneously. They're different blocks, and I'm a miner. I'm gonna look at both blocks and I'm gonna say, okay, cool. I see these two people propose these two blocks. They propose these blocks on top of these chains. I don't know which one to pick because they're the same length, and I can only pick the longest chain. Okay, so I kind of am at like a standstill until somebody adds another block. And then once I add the other block, I say, cool, that's the longest chain. All right, now I can do that. But if this guy over here is actually withholding 2 blocks he already mined, and after I choose this block, he adds those 2 blocks to the end of his, now he has the longest chain. So I gotta like switch back over to this guy and discard everything I did over here. And that's a lot of wasted work, okay? Not to mention, it's a lot of wasted round trips talking to each other. I'm gonna like hear about all these blocks, and then like I'm doing some things with the blocks, or I can't do anything, or I make the wrong choice, and then I gotta switch my answer, and like over time, this like that's why Bitcoin block times are long, right? It has to account for all these things. It has to account for the ability to add blocks that other miners can choose, and you can actually reach finality. So this is also, in addition to Bitcoin, like you could look at kind of proof of stake in a similar way. Like we're just going to have to talk a lot. Me and the other nodes in the system are going to have to make several round trip communications before we're on the same page, right? And the idea here is that eventually everyone gets in consensus. Give it enough round trips of communication, give it enough time, we get into consensus. But with Poem, it's actually proof of entropy minima, meaning for each block proposed, there is a measured entropic reduction. And that's a fancy lingo for saying how much work went into this block. Okay, did you mine the block? Did it have 10 leading zeros with your proof of work solution? Did it have 11, 12, whatever? Okay, let's actually measure that. And then let's actually measure that going all the way back to the history of the chain, right? All the way through the Genesis block. What is the entropic reduction that occurred on this chain? Okay, so this means that because it's proof of entropy minima, I'm always going to choose the block or the chain with the lowest entropy, aka the most work done on it. Okay, so if I see 10 chains pop up, 10 forks, okay, it means 10 new blocks are proposed all at once, simultaneously. And let's actually say every single other person in Denver is also a miner, and they see all those 10 blocks pop up too. Without talking to each other, with 0 round trips of communication, we all make the same selection of which fork we're going to choose. And it's the fork with the least amount of entropy. Okay, we didn't talk about it. We just all said, let's pick this, because that is our rule. Okay, so basically what this boils down to is a better fork choice rule. And like we know, the final boss of scaling is latency. So if we can reduce the number of times we have to talk to each other, then we can reduce our block times and have better finality because of it. Okay, so that's Poem. This is, we're single chain Poem is currently already, like, we don't know. Someone asked me about like the Nakamoto score, for example. I don't know the Nakamoto score. I'm not sure we've computed it, but it is better. It is faster than Bitcoin, and it's faster finality. Okay, and then let's talk about another thing that we innovated called work shares. Okay, so in Bitcoin, I don't know if you've seen this on exchanges, but whenever you transfer it, you wait for confirmations. Okay, confirmations are additional blocks added onto the chain that you were included in. Okay, and normally you see 6 blocks is like the confirmation requirement for Bitcoin, the average, the lowest. The reason it's 6 blocks is because 6 is the minimum statistical sample size. Okay, so that means for me to have any form of statistical finality, I must have 6 samples. Okay, Bitcoin achieves that once per hour. 6 samples happens once per hour in Bitcoin, which means for my statistical finality settlement on Bitcoin, it's going to take at least 1 hour. Okay, we have work shares. And that's actually because we can only sample the hash rate of the network that many times per hour. And the hash rate of the network says, do 51% of people agree with this chain being the chain? Okay, they're going to keep adding blocks to that chain because they all agree. That's indicating or signaling that 51% of the network is in agreement, right? So in Quai, what we say is, well, first of all, it sounds like a lot of wasted work, doing work on forks that are not going to be included, okay? So first of all, we already hate that. But second of all, we want more samples. We want to be able to sample hash rate more frequently. Okay, so we invented this concept of a work share, which is actually structurally very similar to how mining pools work. Okay, so if you're in a mining pool, let's say a Bitcoin mining pool, okay, the difficulty is so prohibitively challenging for me as a small miner to be able to get any blocks. So what they're going to do is they're going to say, let's hook all of our computers up together, all of our miners up together, and act as one miner. We'll split the work, and then we'll split the rewards based on how much work you did. But to know how much work you did, they have to make you do work that is not involved in securing the network, right? They have to give you a cryptographic puzzle and say, solve that. How long is it going to take you? Okay, took you this long. This means you have this much hash rate. Okay, and that's how much work you are sharing with the network. So it's effectively a work share, right? And that's just so they know how to pay you out pro rata. So what we said is, how can we actually just embed that into our network directly, right? So we did, and it's called a work share. And basically what it is there's block difficulty, similar to how all proof of work works, but there's also a lower difficulty cryptographic puzzle you can solve, let's say 1,000 times lower and challenging, and you actually still get paid for it. Okay, like if I get this less challenging work puzzle and I don't get the block, let's say a block gives you 10 Quai. This might give me 1 Quai, right? And on average, there's 8 of these per block. Okay, but there's an additional thing. Okay, so first of all, that means as a miner, I get paid out 8 times more frequently than I do if I'm just mining blocks. That's one good thing. The second thing is because there's 8 of these on average per block, plus the block, I get 9 samples every 5 seconds, not 6 samples per hour. So our statistical finality is 1 block, not 6 over the course of an hour. 5-second statistical finality versus 1 hour. Okay. Okay. Let's talk about proof of entropy minima again. Let's talk about why anyone would even care to include work shares, for example. So if I attach a work share to a block, that counts towards my entropic reduction. That's work that's not wasted. Even if I didn't get the block, but I got something close to the block, that's still work that secures the network. Because if I have 8 of these work shares, all being calculated weighted in my entropic reduction of that block, if I propose a block with 8 work shares, someone else proposes the block with no work shares. Remember how we all know how to pick? We all pick this one, the one with work shares. So we're incentivizing people to sample the network hash rate more frequently, and we're incentivizing people to get paid out more frequently, right? It's kind of like a win-win-win-win for everyone here. It just makes sense to incorporate. And it's a naturally decentralizing mechanism in the mining pool. You don't have to have big mining pools to compete. You actually have a chance of having or said a different way, you might still want to join a mining pool. But there isn't winner-take-all mining pools like there are in Bitcoin effectively, right? Like in proof of work, exactly. Smaller pools can still get paid out, again, 8 times more frequently, or individual miners, than if they were to just get block rewards. Okay, so paid out more frequently, more statistical hash rate samples. You have a statistical finality in 5 seconds in a single block, and we're incentivizing people to do more work securing the network. We're not wasting work. All work contributes to securing the network, not just block work, not just the final answer, but all 8 sub-answers of that final answer.
I like that. That's very cool. Very cool.
So also why on like Quai Scan you'll see multiple rewards.
That's right. So in Quai Scan, our block explorer, you might see like block fees, right? And you might see like this guy got 10 Quai, but then like all these guys got like 2 or 3 or whatever, you know, the work shares for that. You'll get paid proportionally more, right? There's actually an equation that expresses how much does the block winner get and how much does each work share winner get. Okay, it's based on how many work shares, right? If a block has 0 work shares legitimately because someone got the block early, for example, then the block winner gets 100% of all mining rewards. Whereas if there's 8 on average, right? Because of the way that the difficulty threshold is structured, right? I think it generally is 4 leading zeros less than the block requirement. And that's kind of how you end up with 8 on average. Right, so if you were, for example, to get 1 work share, then the guy who won the block, he might get 90%, and this guy might get 10%. If you get 8 work shares, maybe like the work share guys get 40%, and the block winner gets 60%. Right, so there's sort of an equation there. I'm not giving exact numbers here on what that equation is, but the idea here being like everyone's getting paid out more. So.
Super cool. Gonna have to dig a deep dive into Quai Network here.
Cool.
For sure.
Sweet. Yeah, guys, this has been great. I would love to connect with you guys. We can talk more. I think there's definitely more synergies between Quai and Secret and Autonomous here. So
Absolutely.
we should just connect and just build cool shit.
Yeah, definitely.
Yeah, thank you so much for the workshop. It was
Yeah, thank you.
Of course, guys.